Chapter 9, we dealt with equations and graphs of parabolas, ellipses, and hyperbolas. We also rotated these, and we did polar equations of these. You like this, but wasn't a major topic. We tested and quizzed on that enough, and obviously we're not going to do a rotation on the final anyway. So these are the main takeaways you need from Chapter 9. Again, here's how we got the shapes. So we took a conic and we basically cut it at different angles. You've explored circles before. Ellipses are at an angle. Hyperbolas are at an angle where you catch a base. Hyperbolas are perpendicular to the two bases here. Here is the equation for parabolas. Obviously, these have H and K as your center or vertex, however you want to think about it. If it's an x squared, we know it opens up or we know it opens down. If it's a y squared, it opens sideways or the other way. We said A was always the focus. So if we take these three dots here, if this is our vertex and this is our focus, we called this distance A. We also had the exact same distance back to a directrix, which every point on the parabola is equal distance to the focus and to the directrix. So then we said coming through the focus here is that latus rectum line, and each of these is 2a. So then we made our parabola curve coming out through that there. And another thing you can do is you can plug in specific coordinates and then solve. So for example, you could plug in a value for y here, so you'll know one of the values. For y, you plug that in, you solve for x, it'll tell you the 2 points. You'll know an x equals line, like in this case, and then you can plug that in, and you can come back and you can solve for y there. Here's an example of completing the square with parabolas. So we know, again, it's parabola because it just simply has one squared here. We know it's an x squared, so it's going to open either up or down. You can see all the work here. We complete the square, we get it to here. We would then take this equation and say 4a equals 8. So when a equals a 2, that'll help us find our focus based off our center from opposite of x and y. Then we can plug in some other values and use what we know for equations, or either manipulating the two a's to get the lattice line. Next, here's our ellipses. So two different ways. They either open sideways. So if the major axis is the x-axis, it's always the bigger number A is under there. Ellipses are always plus. And then B tells you how far up and down on the minor axis here. Okay, and then here's a picture with all your points. If it looks the other way, if it opens up on the y-axis, the y still comes second. You could move it to first, but the big thing is the A switches places. So plus sign and then the bigger number will always tell you the axes for these. Center, foci, and vertices for all of these. You can see which Pythagorean identity we use up here. In this case, it's a b squared equals a squared minus c squared, and that comes from this picture here. So we said distance from center out to a vertex, we always call a, but ellipses have foci on the inside, so that's the c. So this distance from here to here is the same as here to here. So it's not a true Pythagorean identity in this case, as far as the variables go, but you can draw those pictures in and find that. Here's an example completing the square for an ellipse. We know it's an ellipse because it has an x squared and a y squared and a plus sign. If it was a minus, it'd have to be a hyperbola. So we go through all the work completing the square. You'll get to this point right here. Equations always equal 1, so you want to make sure you divide by 36. And we get here, and then over here on the sides, all the work to find everything else. Okay, coming from the equation. So we have A, we have B. You'll have to find C, you'll have to do a picture, maybe grab some decimals and get all of these points here. Last shape we have is hyperbolas. So pretty much same equation as an ellipse. We just had the minus sign there. That's the dead giveaway. These are hyperbolas. If your x squared is first, that means it opens up on the x-axis in this direction like this. This distance is always an A, center to focus, and then we're going to go up B to create this box to get the asymptotes in. And then this distance here comes out to be C. So this one is a true Pythagorean theorem. Hyperbolas going the other way. So now the y squared is first because they both open up on the y-axis. Again, it's subtraction. A and B don't necessarily move. Okay? Just because one's bigger doesn't mean that's the axis. It all is determined off of this. So here's our picture backing up why it is a true Pythagorean theorem for this. So this distance C is the same out to here because it just moves along that curve on that circle. Here's an example completing the square for a hyperbola. We know it's either ellipse hyperbola because x squared and a y squared. You have a subtraction sign. So you complete the square, being very careful to change some signs when you do factor out a negative, complete the square correctly, and you get here. Okay, x squared is first, so this opens on the x-axis. So it's going to open like this and like this. It doesn't matter that this is the bigger number. Okay, so a squared is 4, b squared is 16. Here's all the work over here. It is a true Pythagorean theorem, so we can grab the C. You can grab all of your other points here as well. Some important things for this chapter are those 3 shapes. Obviously your equations, any a squared, b squared, c squared relationships, and then any notes to help you figure out which axis they're opening on and how we want to graph these. So that is a quick recap of all the important stuff we did in chapter 9. Make sure you have that on your note card.